a.m. to here. I wish I could have woken up earlier this morning to listen to the first talks of the day. Mm. So um, I'm particularly happy to speak in honor of Michel's birthday because he was very uh, he was very helpful to me and encouraging, um, especially to someone who is coming from outside his immediate field. Uh, because I was inspired by his papers and wanted to understand his work in a different way. And I think that the the work that I want to speak about today is a is a is a finally is a way of actually understanding it. There are many holes, there are many kind of unknowns in this project, but I hope that that they will. I hope that you'll see kind of how to think about these non-commutative algebraic varieties in a different way. Okay, so the motivation came from what I spoke to Michel 15 years ago about, and it's about these generalized complex structures that were introduced by Hitchin. And the idea of a generalized complex structure, to remind people in case it has been a while, is that we have a complex structure not on the tangent bundle, but on the sum of the tangent and cotangent bundles. And this sum, this larger bundle, has an integrability condition. It has a bracket, which is an extension of the Lie bracket, and this is called the Courant bracket, and we just require integrability with respect to this bracket. And the interesting thing about this structure, when you first encounter it, is that there are two extreme cases. There is the case where T is sent to itself and T star is sent to itself. And then there's the case where T is sent to T star and T star is sent to T. Those are the two extreme cases of this type of geometric structure. And it turns out that those two extreme cases are exactly complex structure and a symplectic structure. And this may seem like an oddity or maybe a coincidence, just an algebraic oddity, until you realize that even the integrability condition specializes to the correct things, namely that omega is closed or that the Neuenhaus tensor of I is 0. So, well, okay, I'll speak about what happens in between here in a moment, but there are structures that are interpolating between these two extremes. Now, one of the first things that we studied was the deformation theory of these objects. So one obvious question was, if I started with a symplectic form, and if I wanted to deform in the moduli space of these structures nearby, what could I obtain? And the answer is that you get a complexified Kähler class, as physicists call it. So that this had maybe twice the dimension that you may have expected because of this B-field deformation that occurs here. The one that I want to focus on today, however, is what happens when you deform from a complex structure to a nearby generalized complex structure. It turns out that the deformations of this structure are given by, or at least the tangent space, are given to first order by these groups, these holomorphic cohomology groups. Here you'll see the usual deformations of complex structure, H1 of the tangent sheaf. And then you have two additional components which explain how to move away from the classical complex locus into this more generalized moduli space. You get the so-called Gerby deformations, or you get what we were calling the non-commutative deformations. You get bivector fields. Okay. And the nice thing is that these two deformation theories, they coincide with deforming the two-dimensional sigma models that occur in these cases. So in the case of a symplectic manifold, we have the A model, which is studied in Floer theory. This is a topological quantum field theory, and it has deformation theory exactly given by this group. And similarly on this side with the B model, what we normally think of as the derived category of coherent sheaves with the Hochschild cohomology given by this sum of groups. So the main question. Well, okay, so let me explain this deformation here, this so-called non-commutative deformation. Oops. So it looks like this. So if I have a bivector, I can write it in terms of its real and imaginary parts, and I can put the imaginary part into the top right corner of the matrix. Now you see that this sends T to itself, this sends T star to itself, and this I think of as a map from T star to T. And as long as Q is because Q is the imaginary part of a 2-0 bivector field, it turns out that this thing squares to -1. And is integrable if and only if this is holomorphic and this bivector is Poisson. So this holomorphic Poisson structure gives rise to a deformation of the generalized complex structure where this thing is turned on. So we go from complex to holomorphic Poisson. And the question that I'm asking here is the same as the one that we talked about 15 years ago, which is, can this fact be used to give a geometric approach to non-commutative algebraic geometry? Can we somehow explain these non-commutative rings using generalized complex structures? And of course, the main inspiration for me for asking these questions were these two papers of Michel, where he, Artin, and Tate made a detailed study of certain regular algebras which would deform the polynomial ring, deforming, for example, CP2 or CP3 to a non-commutative version of the projective space. And the interesting thing was that these were controlled by automorphisms, line bundles on elliptic curves. So the goal of this project is eventually to put these papers into a new light, or at least to interpret them from the point of view of generalized complex geometry. Okay, and oops, I think I missed the title. Okay, and the result of the last few years of development in this area is this paper, which was just put up last month, together with my former student Francis Bischoff, who's a postdoc at Oxford at the moment. And it somehow puts together all of the ingredients into a coherent approach and implements this approach in a very simple case where which I'm going to explain today. So basically, I'm just going to try to explain very briefly in this talk what our proposal is in this paper. Okay, and this is just a diagram of the project. I don't expect you to read through the slide right now, but basically the idea is that we're going to kind of try to interpret the usual construction of the homogeneous coordinate ring of an algebraic variety in terms of geometric quantization. And so what I'm going to describe in the following slides is kind of a reinterpretation of the usual Kähler case of how we build the homogeneous coordinate ring. That's supposed to be this box. And we could try to deform, as I just explained, to a generalized complex version of that usual homogeneous coordinate ring construction. But this will be blocked. There's going to be a problem here which we cannot solve at the moment. So instead of a direct attack, which is what we tried a long time ago, we're going to take this usual understanding of the homogeneous coordinate ring and we're going to rephrase it in a completely different way using symplectic geometry. So this will be a symplectic approach to understanding the homogeneous coordinate ring. And it turns out that this symplectic approach is the one that can be deformed. So let me explain how this works. Okay, so this is one way of thinking about a homogeneous coordinate ring. You start, instead of starting with a complex manifold, start with a Kähler structure on that complex manifold. So imagine that you have a symplectic manifold, and suppose that it's pre-quantizable. So its periods are in the integers, and we have a pre-quantum line bundle with curvature omega. One of the ways that you could geometrically quantize this is to choose a polarization. And the most popular kind of polarization is a complex structure. You choose a complex structure, which is compatible with the symplectic form. That makes this connection have curvature of type 1,1. You take the 0, 1 part of this connection, and that defines you a holomorphic structure on the bundle, and you take holomorphic sections. Okay, and that gives you a vector space, which is supposed to be the quantization. Now, in the best possible case, you would expect that this quantization is independent of the choice of polarization. And so you would expect that this vector space would be independent of the complex structure. However, what you can do in order, on the other hand, what you could consider is this quantization, but for powers or multiples of the symplectic form. So if you start multiplying the symplectic form by an integer, you're going to get a sequence of these quantizations. The sum of the holomorphic sections of L to the power k for all k. And each, from the philosophy of geometric quantization, each one of these spaces is supposed to be independent of the polarization. But the collection of all of them is certainly not independent of the polarization. It actually completely contains the polarization because of the algebra structure and the Kodaira embedding theorem. So the point is that we can recover, or we can reconstruct the polarization as long as we use it to quantize all of the integer multiples of the symplectic form, and we obtain this tensor structure. And of course, we could think of this, and this is one of the things that Michel emphasized to me when we spoke 15 years ago about exactly this topic, is that you could, there's many different ways of interpreting this. One of the ways to interpret it is to think of it as arising from a single endofunctor of the derived category, the functor of tensoring by a line bundle, and then you just apply it to your structure sheaf object and construct an algebra from this. So the fact that we have an endofunctor is all that is needed, really, in order to construct this algebra. But anyway, the idea here is that what I'm going to do is I'm going to deform the polarization. I'm going to keep the symplectic structure fixed. I'm still going to try to quantize the symplectic manifold. But the polarization is the thing that is going to change. Sorry, the complex polarization. Okay, so, but before doing that, so this approach to obtaining the homogeneous coordinate ring is exactly what's in this box. It's the usual Kähler approach to getting the homogeneous coordinate ring. Now I'm going to explain how to kind of rethink this same exact construction, but from the point of view of the cotangent bundle of the Kähler manifold. So instead of working on the manifold M, the Kähler manifold M, I'm going to now work on its cotangent bundle, which has a canonical real symplectic form. Inside this cotangent bundle, there are two important branes, as physicists call them. One of them is a usual Lagrangian object, which is just the zero section. And branes always should come equipped with certain unitary line bundles. In this case, I'm just going to take the trivial one. Okay, and this cotangent bundle, this symplectic cotangent bundle, has a second brane, which is called the canonical you could call it a space-filling brane, because the support of the brane is not Lagrangian, but it is the entire space. These types of larger branes in symplectic manifolds, they are called coisotropic A-branes, and they were discovered by Kapustin and Orlov. The idea is that the Fukaya category should be slightly enlarged to include these A-branes. But anyway, what is this thing? It's basically the pullback of the pre-quantum line bundle from M to the cotangent bundle. You pull back the unitary connection, and you add to it the real part of the holomorphic symplectic form that this space has. So we use the complex structure to endow T star M with a holomorphic symplectic structure. We take the real part of that and add it to this. And as a result of this, what happens is that by combining this space-filling brane with the background canonical symplectic form, what you end up with is a holomorphic symplectic structure on the cotangent bundle, which is not the usual one, but it's the one that is twisted by the Kähler form. So it's what is normally called a twisted cotangent bundle. Okay, so this is the idea that there's an additional structure on the cotangent bundle of the manifold, which is basically the fact that I can equip it with a holomorphic symplectic structure, which is the twisted cotangent bundle associated to the Kähler form, and that's how I'm using the Kähler form. I'm using it to construct this twisted holomorphic cotangent bundle. And basically, when you intersect these two branes, you obtain and take the difference of the connections that are defined on them. What you end up with is the restriction of this twisted holomorphic symplectic structure. You restrict this to the zero section, and when you do that, you reconstruct the Kähler form, because the canonical symplectic form just restricts to zero.
Excuse me, may I ask you a stupid question?
Yes.
This little omega and capital omega zero, what's the difference?
So the imaginary part of this capital omega, so okay, let me just write. So this is the holomorphic symplectic form on T star M, and the imaginary part is the canonical symplectic form in the real sense. So I'm thinking of T star M as a real symplectic manifold, but because of the complex structure of M, it inherits a holomorphic symplectic structure. That's omega naught, capital omega naught.
Okay. Mm-hmm.
Okay, but there's a second holomorphic symplectic structure on it, which is the one that is obtained by twisting it by the Kähler form, which you pull back from M. Okay, and these are non-isomorphic complex manifolds. Both basically, from a smooth point of view, they're just the cotangent bundle. Okay, and right. So the picture is the following, that on the cotangent bundle, we have two branes. One of them is Lagrangian, and the other one is space-filling. The proposal would be that if you have two branes in the A model, you can compute the homomorphisms between them. They're supposed to form a category. And so I should be able to produce a vector space, which is the homomorphisms between this Lagrangian and this space-filling brane. And that indeed gives us the result we expect, the holomorphic sections of L over the manifold. But I just want to emphasize that this would be a kind of Fukaya Hom, okay, in the Fukaya category from the point of view of symplectic geometry. The only reason, I mean, the problem with this is that in the people who study the Fukaya category intensively, they don't usually include these coisotropic branes that Kapustin and Orlov told us exist in the Fukaya category, or at least in the category of boundary conditions for the A model. So anyway, this is a symplectic way of computing a sheaf cohomology group on the original manifold. And then we can take advantage of the fact that this space, T star M, has a algebraic structure. It actually is group-like in the sense that we have an addition operation on the fibers of the cotangent bundle. That is making it into what's usually called a symplectic groupoid. And so because of the fact that this is a really simple example of a symplectic groupoid, that means that we have a Lagrangian relation between the product of it with itself and itself, and it's an associative Lagrangian multiplication structure on this symplectic manifold. And it allows us to define a convolution of the branes inside it, any object inside it. And this convolution will satisfy these conditions, that the zero section, of course, when you add it to itself, you get itself. And this space-filling brane, when you convolve it with itself, you actually get the space-filling brane that would correspond to L squared, the square of the pre-quantum line bundle. So basically, we can understand the algebra structure that is formed from these two branes in the following way. We understand it as taking advantage of a basically a monoidal structure on the Fukaya category of this symplectic manifold. This monoidal structure allows us to take these two objects and square them, cube them, and produce a sequence of pairs. L and B, L squared and B squared, L cubed and B cubed, and so on. Okay, so we produce a sequence like that of L and B, L squared and B squared, L cubed and B cubed, and so on. That's what we use the monoidal structure for, and that is coming from the addition structure on T star M. And then we can take basically HOMs between these pairs, HOMs at each stage, right? And because of the monoidal structure, this will form a graded algebra. And it's the graded algebra that we expect. Now, I just want to point out that this idea coincides with another development in the physics literature. Witten worked with Gukov in 2008 and has continued this work, culminating in this recent paper by Witten and Gaiotto, where they have a new approach to geometric quantization, which is exactly of this flavor. Their basic idea was that whenever you're trying to quantize a symplectic manifold, what you should do is construct an auxiliary space which has twice the dimension. They call it the complexification of the symplectic manifold. And then in that symplectic manifold, which is twice as large, you should have two branes, one Lagrangian and one space-filling. And then they argue that the homomorphisms between those two branes should give the geometric quantization. So they were not using it exactly in the way that I am here, but it is extremely similar, and we were inspired very much by this original paper of Gukov and Witten. Both of these papers are very interesting and provide a kind of new way of approaching quantization. Okay, and so that is exactly what I meant by moving from here to here. So the idea is that instead of having a pair of objects in the derived category, or B-branes, and then taking HOMs in the derived category between these objects, what we do is we promote these to branes in the cotangent bundle of the symplectic manifold, which has a canonical symplectic form. So we're not using the symplectic geometry of the original symplectic structure. We're using a kind of canonical symplectic structure, and we are using the data of the complex structure and the symplectic structure to produce branes in an ambient symplectic manifold, which is twice as big. Then the homomorphisms between them give us the same result, but I'm in a different category. I'm in so-called A model. And then the tensor product of these A branes comes from the fact that the space itself that I'm using has some kind of monoidal structure. It's a groupoid. Okay, and that gives rise to a graded algebra, which is the same as that one. So this is the cotangent lift construction, I would call it, converting B model into A model in a certain simple way. Now I'm going to explain how this should be deformed. So I need to now change the polarization from a complex structure to a generalized complex structure, and I need to see how this thing is going to be modified. What we're going to see is that this cotangent bundle changes dramatically. It changes to what is called a symplectic groupoid. Okay, so right. So maybe I should explain first why we cannot. Let me briefly explain why we cannot easily pass from the left side directly to a direct kind of deformation of the B model using generalized complex structures. So let me do that first. So, and this is older work. This is older work that was kind of blocked, and I'll explain what the problem was. So if you take this deformed complex structure using the Poisson structure, then you can study the concept of a brane on that. So there should be a category associated to this, which would be a deformation of the B model. You could study the objects of this category. And these would be line bundle, let's say branes supported on the entire manifold. They would be a brane with a unitary connection satisfying a certain condition. The curvature would not have to be of type 1,1, but rather, if this were 0, it would be of type 1,1. But because of the presence of the Poisson structure, the type 1,1 condition gets modified. And then it turns out that there is that as long as the pre-quantum line bundle, as long as this line bundle is a holomorphic Poisson module, okay, which just means that the Poisson structure, the holomorphic Poisson structure sigma, should lift to the total space of the line bundle. As long as that condition holds, then this brane, this pre-quantum line bundle that we're used to in the Kähler case deforms to such a brane. And there's a nice construction of it where we have to average the typical Chern connection by the action of a Poisson vector field. So you can see how the integration of a Poisson vector field, an object in Poisson geometry, is being used to construct this brane object. And then we also have the structure sheaf, which would be a trivial brane. So we obtain two branes on this deformed complex manifold. Okay, I call them the trivial brane and the deformed pre-quantum brane. The quantization should be the homomorphisms between them in some category, which is some kind of deformation of the B model. And we could even view this as an autoequivalence, which takes any brane, pulls it back by this flow of a Hamiltonian vector field, and tensors it by this brane B1. And we could iterate this and construct a whole family of branes. And if we only had a category here deforming the B model, then we could just take the Homs between them and get our graded algebra, which we would expect to be the non-commutative deformation. Okay. The problem is that we have no definition of this category. If you look in the physics literature, there is no suggestion somehow analogous to the B model and A model calculations, which indicate how one should compute in this category, the morphisms. So this is the main reason why the deformed B model approach is stuck. So instead of going directly this way, we're going to kind of take this detour to this. So let me explain how this works. So whenever you have a generalized complex structure, and this is work that has been done, since that time. So we needed, in order to even perceive this detour, we needed to learn a lot about symplectic groupoids from the point of view of the Weinstein school of Poisson geometry. So any generalized complex structure has inside it a real Poisson structure in the top right corner. And we're going to assume that this real Poisson structure can be integrated to what is called a symplectic groupoid. So this is a manifold, a symplectic manifold, with maps down to the original Poisson manifold, which in a certain sense desingularize the Poisson structure. So if this Poisson structure on M has various symplectic leaves of various dimensions, then all of that complexity is kind of absorbed into a single symplectic manifold and a map. And if you push forward the symplectic structure above down to the base, you'll get the Poisson tensor. But it's not just a kind of resolution of the Poisson structure. It actually has a richer structure. It can be thought of as, each point in this auxiliary space can be thought of as a path inside the base manifold, a path up to homotopy. And it's not just any path, but it's a kind of Hamiltonian path. We use the fact that M is Poisson to generate a kind of Hamiltonian paths, which remain on symplectic leaves. And those paths have a source and a target. And that's the source, that's the reason that this manifold is equipped with two maps down to the base. So this is, in a way, a moduli space of a certain type of path in the Poisson manifold. And because paths can be concatenated, these types of paths, can be concatenated, that's why this space has a groupoid structure. So it's a canonical groupoid that is associated to a Poisson structure. And that's what we will construct. In general, you can only prove that this groupoid exists in a neighborhood of the identity bisection. But in many interesting cases, the groupoid exists globally. And so you get what's called a complete integration, or a complete symplectic groupoid. That basically depends on all of these Hamiltonian paths being complete. In other words, like if I give you a Hamiltonian function and you construct the Hamiltonian vector field, the assumption is that that Hamiltonian vector field is complete. That's not quite enough in order to obtain this groupoid, but it's one of the assumptions that we can easily make in many interesting examples. And by the way, in the case that the Poisson structure is zero, this symplectic groupoid is in fact the cotangent bundle that I used before. But you should think that both maps are the same projection map down to the base. So the source and target fibers, which I tried to draw here in red and blue, they would agree in the case of the cotangent bundle. And if you turn on a non-trivial Poisson structure, they separate and become two different foliations of this symplectic manifold. So so the key properties that I'm going to use is that, first of all, the identity arrows inside this groupoid form a Lagrangian brane inside this symplectic groupoid. So it's a Lagrangian. And the other thing I'm going to use is that if we look at the combined source and target map, which map the groupoid to M cross M, it turns out that this map is compatible with the generalized complex structure. This was a fact that was noticed by Marius Kreinik in one of his papers on the subject of generalized complex structures. Basically, it means that the symplectic geometry of the groupoid and the generalized complex geometry of the manifold are very closely related. Okay, and the map is a generalized holomorphic map. And what this means is that if you give me a pair of branes, one in the left factor and one in the right factor, you can pull these back and you will get a brane in the symplectic manifold. So that means that for any pair of branes, I get an A brane inside the symplectic groupoid. Okay, so this means that we have a potential kind of way of resolving the problem. We can take this undefined group on the generalized complex manifold, and we can define it as being the morphisms in the A model between the identity bisection, this kind of idempotent object, to this brane that we obtained from combining the two branes in question. Okay, and then we can make use of the fact that we have a multiplication which, just like in the cotangent bundle, is compatible with the symplectic structure, and which allows us to convolve branes. So we could just take this brane, this BJI brane, and convolve it with itself, just iterate that construction. And we obtain a graded algebra in theory. As long as we can construct these homomorphisms, we obtain a graded algebra. And this graded algebra is very clearly, has no reason to be commutative, because it is based on, now it is based on a groupoid that is non-trivial, where certainly the structure of the groupoid is nothing like the cotangent bundle. These arrows actually do not have the same source and target, and so they can only be composed assuming that they are composable. And so the commutativity would be very surprising for such an algebra. This is a kind of categorical version of, well, I guess what I should just say to this audience is that it's because of the fact that this is a symplectic groupoid that its Fukaya category should be monoidal. And so I'm using this monoidal structure on the A model.
Excuse me.
Yeah.
May I ask a question?
Yes,
when you talk about the proposal for defining the home space for a generalized complex structure, can it be reduced to the case that when the generalized complex structure is taken to be an ordinary complex structure, and with the home space,
with the home space being
the home space in the derived category of coherent trees?
No, because so the point is that you're deforming away from the complex locus, and the generalized complex structure is no longer a complex one. It's a deformed one. It's not equivalent to a complex structure. So the generalized complex structures have this hybrid nature that in some regions of the manifold they could be symplectic, and then that symplectic structure degenerates in a certain submanifold to a complex structure. So yes, so it's, there is no derived category present in order for you to actually construct this home space.
So you mean that in this case you're talking about those complex structures, but not the one induced by the ordinary one.
Yeah. So so if it wasn't clear already, so the idea is that if you start with a complex manifold and you give me a holomorphic Poisson structure, you can deform that thing to a generalized complex structure. Okay, and it's no longer complex.
Yeah.
So we've left. It's like that you're deforming the geometry into a different direction. And with that new geometry, you would like to construct a category like the category of coherent sheaves.
Yeah.
That approach doesn't seem to be available at the moment.
Yeah.
Okay. So I'm kind of providing an alternative route which appears to work much better.
Yeah. Okay. Thank you.
Yeah. Right. So anyway, the point is that we are going to lift the computation to this symplectic groupoid. We're going to convert the pair of objects that we want to take the Homs between to a single object. Okay, and then we have this canonical identity bisection, and we take Homs between the iteration, the iterated convolution of this brane with itself. Okay. So, okay, this provides a possible solution to the problem of how to compute homomorphisms between generalized complex branes. But it runs into a serious problem, and that problem is that the practitioners in symplectic topology do not consider these types of space-filling branes in their formalism. Despite the fact that they do exist in the Fukaya category, or at least they should exist in the Fukaya category, at the moment, the way people study the topic is that they consider only Lagrangians and the various categories that these Lagrangians generate. But it has been known now for a while that if you really want mirror symmetry to hold in full generality, you will have to extend the Fukaya category, and it will have to include these additional objects. But so basically, we reduced our unsolvable problem to another problem which has not been solved, which is how do you compute the morphisms in the A model between a Lagrangian and a space-filling brane? And so we have to provide a proposal for that as well. So if you have a Lagrangian and a space-filling brane, to compute the homomorphisms between them, we have no general guidance from the physics literature. However, we do have about 3 or 4 papers where these morphisms have been computed in the physics literature. They were computed by Aldi and Saslow in 2006 in one example, by Witten and Kapustin in a very important example on the Hitchin moduli space, and by Witten and Gukov in a few examples, and similarly in this recent paper of Witten and Gaiotto. And in each case, they had what I would say is a very tailor-made solution. It's kind of ad hoc for the problem at hand. There is no general way, and I'm going to propose a slightly more general method, which involves using the fact that this space-filling brane provides this symplectic manifold with the structure of a holomorphic symplectic manifold. So this brane on this symplectic groupoid gives the groupoid the structure of a holomorphic symplectic groupoid. So we have a holomorphic symplectic structure on this groupoid. And the idea is what we should do is to choose a holomorphic, we should basically use a holomorphic version of geometric quantization. We should foliate this thing by holomorphic Lagrangians, and then choose a holomorphic prequantization of the connection, a holomorphic prequantization of this holomorphic symplectic structure. And then we should do what is normally done in geometric quantization, which is to take flat sections along these Lagrangian leaves when possible. So if you have a Lagrangian leaf for which the holonomy of this connection is 0, we call it a Bohr-Sommerfeld leaf, and we take a sum of these. And this agrees with the ad hoc, this is maybe a slightly more general, slightly less ad hoc definition, which actually coincides with all of the cases that have been computed until now. And then we need to hopefully make this computation of Homs between these two branes in such a way that we can follow the computation when we do this iterated convolution. So we need to make sure that the prequantization of this holomorphic symplectic structure on the groupoid should be compatible with the multiplication with the groupoid structure. And that's why we need a multiplicative prequantization and a multiplicative polarization. So this seems like a tall order. It consists of, well, here I've just drawn the multiplication relation between the groupoid, on the groupoid, and the idea is that we would be prequantizing, so we would have a holomorphic line bundle with a holomorphic connection on G, and we would hope that that is compatible with the multiplication, and that's what this multiplicative cocycle provides. So we were able to, in our recent paper, we were able to implement this in the case of toric varieties. So if you take a toric Kähler variety with a prequantization and a linearization of the toric action, so that the torus is acting on the prequantum line bundle. So this is a usual toric Kähler variety. And what we do is choose an R matrix, a so-called R matrix, which is just a tensor in wedge 2 of the Lie algebra. And this gives rise to an invariant Poisson structure on this toric variety. And so it gives us a deformation in the non-commutative direction. And what we can do is take advantage of the fact that in the Poisson literature, namely in a paper by Ping Xu, there's a very explicit description of the groupoid. The groupoid happens to be the cotangent bundle